In the last few lessons, we've been writing a polynomial to fit a function, but not all of those polynomials fit the function perfectly for every x value. So we're off by a little bit. What these next two units are going to be discussing is how far off are we from the actual value. So we're looking at what's called the LaGrange error bound. First of all, p sub n of x, that's the polynomial, it's the nth order Taylor polynomial for any specified function. The nth order, so that means the nth derivative used to create that polynomial. R sub n of x is the remainder, or the error, how much we're off. It accounts for the disagreement between the actual value of f and the value we get by plugging that number into a polynomial. So we're off by a little bit. And R sub n of x is how much we're off by. For any x value then, if I wanted to find the actual function value, I would take the value of the polynomials. So if I were looking for sine of 0.5, which we'll do later, I would plug 0.5 into the polynomial, and that would get me close. But if I added on this little remainder, that would get me exact. Now if I could find that remainder, why would I ever even need to use this polynomial? So we're finding an error bound. We're going to say, well, here's what we think the answer is, plus or minus a little bit. So we're close, but we're off by a little bit. All right, let's talk a little bit more about that. This is a third degree polynomial for sine x. And when we talk about the remainder, we're talking about the distance between these two functions. So how far off are we? This would be the remainder. That's the difference between the actual function value and the polynomial's value. Now you could see that this is a Maclaurin polynomial for sine. This was centered at 0. And if I plug in something like 2 into the polynomial, if I'm trying to find the sine of 2, and I plug 2 into the polynomial, I'm going to be pretty far off. That's a pretty big gap between the function itself and the polynomial I wrote. So there are two things we have to keep in mind when we're trying to find a closer value to the exact. So this remainder is off by a bit in two situations. The magnitude of r, so how much r is off by, depends on, first of all, how many terms we have in the polynomial. So the more n increases, in other words, the more terms there are in the polynomial, the more r decreases, the closer we are to an exact value. So if I would have used more than just a cubic function here, if I would have had like a 7th order polynomial for sine x, then plugging in 2 to that polynomial might have gotten me a little bit closer to an exact value. The other thing I have to think about is x. The further away we get from x, the more r increases. So if I were to use this Maclaurin polynomial, which is centered around 0, and plugging in 2, I'm much further away from that center point of 0 than I should be to get a good approximation. So the farther away I get when I plug in values, like 2, if I were to plug in 3 is even farther away from my center point of 0, my remainder is going to be even bigger. In other words, it's not a good estimation. All right, let's start looking at this remainder. We're gonna talk about it a little bit in this video, and then we'll formalize it in the next. I would like you to write a third order Taylor polynomial for to estimate e to the 0.1. And then I want you in the second part to put e to the 0.1 into your calculator. And then I want you to find the difference between them. What is the remainder with those two? Okay, welcome back. Let's see what you did here. If we write, first of all, the third order polynomial for e, let's do that first. So e to the x is approximately this third order polynomial, and the third order polynomial for e to the x is 1 plus x plus x squared over 2 factorial plus x cubed over 3 factorial. So this is one I would expect you to do without a calculator. We're just trying to estimate based off of our own recollection, our own mathematics. So now if I'm trying to evaluate e to the 0.1, I'm going to replace all of the x's with 0.1. I'm going to write this as 1/10, so it's easier for me to do without a calculator. Okay, so let's do some math here. We've got 10/10. Well, I'm going to hold off on that because I know I'm going to need a bigger common denominator. We've got 1 plus 1/10. 1/10 squared is 1 over 100 plus, or over 2 factorial, so this becomes 1 over 200. 1/10 cubed is 1 over 1,000. 3 factorial is 6, so this is 1 over 6,000. Yikes. Getting a common denominator then. I have 6,000, and then 600 times 10, so that's 600, plus 30 times 200 is 6,000, plus 1. So I have 6,631 over 6,000. That's my approximation. I think e to the 0.1 is not equal to that, approximately that. Okay, putting e to the 0.1 into my calculator, I get this. Also an approximation because the calculator rounds, but a much closer approximation. I'm going to go out quite a few decimal places just so we can compare. All right. Now, I'm going to find out how far off we were. I'm going to take our approximation, 6,631 divided by 6,000. So I'm going to actually get that as a decimal now. And I know this defeats the purpose, but when I put my approximation into the calculator, this is my estimate. I got 1.105, so it's off by a bit, especially because this is an exponential function. 1, 6 repeating. So to find the remainder, this is the remainder then. This was a third order polynomial. To find the remainder of calculating 0.1, I'm going to use the absolute values because I don't really care if we're off by being a little above or a little below. I just want to know what's the distance between them. So if I take my actual and subtract my estimate, that's going to give me the remainder. So let me do that calculation really quickly. Minus point 0.000. Let me try that again. That doesn't feel right. So if I do 6,631 divided by 6,000, okay, I was right. So I've got 1, 2, 3, 4, 5 zeros. 1, 2, 3, 4, 5 zeros, 4, 2, 5. That's a pretty good estimate. Those were pretty close. So my third order polynomial is a pretty close match. But a couple of things are really helpful. First of all, I had quite a few terms. I had 4 terms in my polynomial. And 0.1 is really close to 0. So I had 2 things going for me. I had a higher value of n, more terms in my polynomial, and 0.1, that distance was pretty close. So there's this guy, LaGrange. We're going to talk about him, not just some guy. He's a mathematician. I'm going to bring this graph up. I had it just kind of tucked away for a minute. This is the graph of e to the x and the graph of my polynomial. And you can see, let me shrink it down a little bit. You can see I shrunk it down, look at the x-axis, 0 to 0.5, that these two are really close, all the way up through like 0.6. If you can't tell from this, but the blue one is the polynomial, and the red one is e to the x. So they're almost a perfect fit. And I say almost because we could see that we were off by just a little bit here. So what LaGrange is saying is, if we can find the remainder, if we can estimate that, then we can say how much we're off by. Or if we can come close, then we can say, well, we're within some values. So what he says is that, guaranteed, if I would have gone one more term, so if I would have found the fourth derivative at some value, and I'll explain this in just a second, if I would have found the fourth derivative, so the next term over 4 factorial, and if I would have plugged in 0.1 to the fourth there, I would have, or not 0.1 to the fourth, sorry, this was, the 0.1 to the fourth because this was a polynomial, I would have been able to find the exact value of e to the 0.1. So the problem is this. We don't know exactly what that is, but what he says is, if I can find a number somewhere between 0 and 0.1, I know for a fact, or he knows for a fact, that somewhere between 0 and 0.1, there is a value z that will make this exactly equal to the remainder that we need to make these two values exactly the same. So he's saying that somewhere in there, between 0 and 0.1, this expression will equal what we were off by, which was 0.1234542, and then there were more decimals, but I'm out of room. So what we're going to say from here on is, all right, we can't find that z value. That would be guess and check. And if we could find the z value, it would take a calculator to do it, and then why don't we just find e to the 0.1 anyway? But what LaGrange is saying is that somewhere in between 0 and 0.1, there is a value z that if we plug that into the fourth derivative, we will get the exact remainder. All right, great. That's his theorem. So let's put that into formality here. So the LaGrange remainder, then, he says the remainder is the n plus 1 derivative, the next term in the sequence, evaluated at some value z, and then in the case of a Taylor polynomial that's not centered at 0, this would be x minus a to the n plus 1. And this is assuming that z comes somewhere between the center and the value of x that we're plugging in. So that's what I showed you in the graph up above. Now that z value will come somewhere between 0 and 0.1, and if plugged into the next derivative, we'll have the exact remainder. Okay, that's where we're going to stop for right now, because in the next video, we're going to formalize this idea.